Hey guys, welcome to lesson 3.2.1 where we are still rewriting to solve and show equivalency, but it's going to be kind of a new take on things. And first we're going to talk about some exponent rules, which you guys might have seen a little bit of in the past, but we're really going to go over that and learn those in more detail today. So here I have in bold all of the exponent rules that we're going to talk about. For the first part here, I want to make sure you guys are aware of what it actually means to have an exponent on a number or even a variable. So like a to the fifth power really means that we're multiplying a by itself 5 times. So a times a times a times a times a. Okay, there's 5 of them because there's a 5 for an exponent. All right, so it's really important that you understand that basic concept before you go to understand all the rules when you're working with numbers that have exponents. All right, so now let's take a look at what happens when we multiply two numbers that are the same, but both of them have exponents. All right, so here we have 2 to the second power times 2 to the third power. Now if we think about how exponents expand, we would know that 2 squared is 2 times 2, and then 2 to the third would be 2 times 2 times 2, right? Again, this is 2 squared, and then this is 2 to the third. Now, the thing is, here we have 3 2's, which just as you saw over here, would mean a number to the fifth power. So here, because there's 5 2's, did I just say 3? Because there's 5 2's, we know it's going to be 2 to the fifth power. Now, hopefully, you would notice that, well, to get that 5, I could have just added the 2 and the 3. So that's actually what our rule is. Okay? Anytime you're multiplying two terms that have the same base, this right here is the base, the a, but they both have exponents, you could just keep the base and add the two exponents together. All right, so right over here, who has time to write 25 2's? Who has time to write 45 2's, right? None of us do. But luckily, we can just say that it is 2 to the 25 plus 45, whatever that ends up being, right? 25 plus 45 is going to give us 70, so we know that this would be 2 to the 70th power. All right, exponent rules make our lives a lot easier. All right, quotient with the same base. Now this is when we have, again, that idea of a base, that's the a. That one is the same, but now they are being divided. Now, thinking again about how terms with exponents expand, we know that a to the fifth over a to the third, I'm going to get my skinny pen here, would be 5 a's on top, all over 3a's. So it's a times a times a times a times a over a times a times a, right? 5 of them over 3 of them. Now, we are pretty familiar with how things can cancel, right? We know that these will cancel to become 1. These will cancel to become 1. These will cancel to become 1. That leaves us with these two. All right, and a times a can just be rewritten as a squared. All right, now hopefully we would notice that a faster way we could have gotten this 2 is by subtracting these exponents. All right, 5 minus 3 also equals 2. So that tells us that our rule here, anytime you have the same base, we could just do, that's an ugly a, keep the base and then subtract those exponents. Okay, so let's apply that here. Who's going to write out 300 or 50 a's, right? Nobody. Nobody has time for that. So instead, we can say that it's going to be a to the whatever 300 minus 50 is. Okay, and that would actually equal 250, so we would get a to the 250th power. All right. Moving on, anytime we have a term that already has an exponent and we raise it to another exponent, let's go ahead and expand this and see what happens and see if we can identify the pattern, right? This means that there's an x squared times an x squared times an x squared, right? Because the x squared was raised to the third power. Let's keep expanding this even more, right? We know that x squared is x times x. This one's going to be again x times x, and one more x times x. All right, so now we are multiplying 1, 2, 3, 4, 5, 6 x's together. So we can just say that this is x to the 6th. Now, a fast way to do that would have been to multiply these two exponents, right? 2 times 3 would give us 6. So sure enough, our rule, whenever we are taking a term with an exponent and raising it to another power, we just have to multiply those two exponents together. Okay, so here, let's go ahead and try that. X to the 10 all to the 5th power would be x to the 10 times 5. That's going to be my new exponent, so it's going to be x to the 50th power. All right. Something important for you guys to note is that anytime you raise any number to the 0 power, it equals 1. Anything at all. It does not equal 0. That is the most common mistake. In college, you might get to learn all about why that is the case. Okay, but anything you raise to the 0 power just automatically equals 1. I know it's weird, but we just have to go with it. All right, negative exponents. So in math, we don't really like negative exponents. So we have a way to rewrite this so that it is no longer a negative exponent. Now, the way I like to think about this is the negative sign is kind of used like a hall pass, okay? Let's first imagine that every number, right? Every number in existence actually has an imaginary denominator of 1, right? You can imagine any number in the world to be over 1 because anything divided by 1 just equals itself. So that's what this looks like right now. And because it has a negative exponent, we're going to use that negative sign as a hall pass to go to the other side of the fraction. Okay, so we will rewrite this where a to the negative b is on the bottom, but that negative sign goes away because we moved it. Okay, that negative sign was like a hall pass that we used to go to the other side, and then you give away that hall pass, right? And because nothing's left on the top, we have to put a 1 up there. It's like a placeholder. So here, again, know that it's always over 1 automatically. This gets to be written as 1 over x to the 3rd power, because this negative sign brings that term to the other side of the fraction. Another example of that would be like if I had, let me do the skinny pen. If I had another example where it's actually already 1 over x to the negative 3rd, this would actually become x to the 3rd over 1, or just x to the 3rd. Okay, so I just want you guys to see that anytime there's a negative exponent, it's just going to move to the other side of the fraction, regardless of which side it is on. All right, the last exponent rule that we're going to be talking about here is fractional exponents, which actually is related directly with radical expressions. And this is something you guys will probably learn more about in college as well, and you might not have ever seen this one before. So here, a to the 1/2 power, the 1/2 exponent is actually just a regular square root symbol, okay? We are all very familiar with the square root sign, but probably very few of you are aware that that's actually a 1/2 exponent, right? So the way that this works is that anytime you have a radical, there's actually two pieces here. So let's just see how this works in an example. If I have a 3 to the 4/5 power, that tells me that I need to put the 3 in a radical. Okay, and then this number, the bottom number is what tells us what kind of radical we are going to be using. So the 5 tells us that we're going to take a 5th root, okay, not like a square root like we're used to. And then the top number of the fraction tells us what the exponent will be for the number inside of the radical. Okay, now if you apply that same rule to this one right over here, it still works. The thing is that square roots always have an imaginary 2 here, we just don't talk about it. And a not having any exponent is the same thing as a having an exponent of 1. Okay, so these two are the same thing. All right, so let's write our rule here. A to the m over n is going to be the nth root of a to the m. Let's get some colors in there. All right. And m exponent. All right. So that's all really the exponent rules that we're going to talk about. Now we're going to work on simplifying some expressions using some of these exponent rules. All right. So here we have some problems. For the first one, we know that we can expand this out to be 3 times x all over x, because we changed that x squared to these two x's. Now we can tell that these can cancel, and so we are left with just the 3x. So this would be the simplified version. All right, now here, I know it might be a little bit uncomfortable to work with like binomials or polynomials instead of just single terms and variables, but it works the same way, right? If there's an x minus 3 down here and there's one up here, we can cancel those. Those would divide out and turn into 1, and we would just be left with x plus 2. All right, here you might be tempted to cross these x's off. However, that does not work, right? The only reason we are able to do that in these two was because there was only multiplication going on. And I know you might think, well, what about the plus and minus? But because they're in parentheses that are being multiplied, it still only counts as multiplication. Whereas here, there is straight up subtraction going on. So instead, we can take a closer look and notice that we can actually divide both of these by 2. So let's go ahead and do that. I can factor out a 2. When we do 2x divided by 2, we're left with x. It's kind of ugly. And then when we do negative 4 divided by 2, we get negative 2. Okay, so we can rewrite it to look like this. And now we can see that both of these are going to cancel, and we're just left with 2. All right. Now we have one more problem, and this is kind of the heart of this lesson actually, or this part of the unit, and that is to simplify this, this rational expression. The steps when you're simplifying a rational expression are to factor everything you can. Okay, that's always the first step. Factor whatever looks like it's factorable. And then once you do that, you can start canceling stuff, kind of like how we did up here or over here. So let's go ahead and start by factoring this guy right here. The bottom one isn't really factorable. The top one, though, that looks like all the stuff we've been factoring for a really long time now. So let's go ahead and box and diamonds this. Okay, so we have x squared up here, 6 over here. Do our diamond. I'm not going through this super slow because we've been doing factoring for so long. 6 times x squared gets us 6x squared up here. And then the middle term, 5x, goes down here. So the two numbers that are going to multiply to make 6 and add to equal 5 are going to be 3 and 2. Okay, so now that we've filled out the inside of our box, we can go ahead and fill out the outside. X times x is going to equal x squared. We get a 3 over here to get 3x, and a 2 over here to get a 2x. So now we can rewrite this whole expression with our new factored form. Our new factored form is x plus 2 times x plus 3. So we can place that back in the original equation. Instead of x squared plus 5x plus 6, we can now write x plus 2 times x plus 3. And then this x plus 3 at the bottom just stays the same. So now we can take this and say, okay, well, there's an x plus 3 on the top and an x plus 3 on the bottom. So these will divide out and turn into 1. So really the simplified version of our expression is just going to be x plus 2. Okay, and now it's like fully reduced. All right, that's all for today.